So often when we move very far away from a charge distribution, what we say is that the potential will look like that of a point charge. Now what we want to do here is to find something a little bit more precise. And what we're going to do is we are going to look at the case of an electric dipole. So for the electric dipole, we have a positive charge and we have a negative charge. These are situated somewhere along, let's say, the z-axis. And this is the midpoint, which will be the origin of our system. The distance between the two charges is equal to d, so the distance of one charge from the origin to that charge is going to be equal to d divided by 2. So now let's say we want to determine the potential at some point P. Okay, now P, remember, is our point of observation. Now since P is our point of observation, our field vector from our origin, which is at the midpoint between the two charges, to that point is given by r. R prime is the distance from the midpoint between the two charges to one of the charges. So here we have an R prime, say in the positive direction. And we also have R prime in the negative. Okay. So the separation vector between the positive charge and a point of observation will be given by R minus R prime, and we're going to put a plus in here, and between the negative charge and our point of observation, it's going to be given by R minus R prime, it's a negative. So now what we could do is we could write out our primes. So R prime plus would be equal to d over 2 z hat. And for the negative, it would be equal to minus d over 2 z hat. Okay, now the angle that our field vector makes with the z-axis is theta. Okay, so what I do here, I just want to write down what the potential of this configuration is going to be, what the potential of a dipole is going to be. So what we have here is just the summation of the potential due to both charges. So we have V of R will be equal to 1 over 4 pi epsilon naught by Q, so it'd be plus Q all over R minus R prime plus minus Q divided by R minus R prime minus. Okay, so this will give us our total potential at this point P due to the two point charges. Now what we can write from the law of cosines is we can write out what the magnitude of our separation vectors are. So we have R minus R prime. I'm going to square it to get rid of the square root on the other side. This for either the plus or the minus. And again, we're using the law of cosines here, so we have a R squared plus d over 2 to be squared minus R plus RD cos theta. Let's take the R outside, so we have r squared into 1 minus or plus d over r cos theta plus d squared over 4 r squared. Okay, now since we're interested in a regime where r, the distance away, is going to be much greater than the distance between the two charges, what we can do is we can neglect this third term, okay? Because this is going to be negligible. And what this is going to yield is if I move it over here, actually. Okay, so what in fact this will yield is 1 over r minus r prime be equal to r by minus r plus over r cos theta is the power of minus a half. Okay. So now what we can do is we can use a binomial expansion, and so if we apply binomial expansion to this, what we're going to have is a 1 over minus r prime. This, in fact, this should be a plus or minus. The plus or the minus term will be equal to 1 divided by r into 1 minus or plus 1 over 2r cos theta. Okay. So now we can go back to the original equation, where what we have is we can have 1 over dash prime for the positive minus, so we're going back to our, the potential calculation, minus dash prime for the minus, and what this is going to give us now is just d divided by r squared cos theta. Okay. So the potential of our dipole system is equal to 1 over 4 pi epsilon naught by d cos theta divided by r squared. What we see here is that the potential in the field of a dipole falls over as 1 over r squared.